Hi,
Hello, good morning.
morning.
Good morning, Ziwei.
Good morning, Mounira.
Hi again.
Hi.
Good morning.
Good morning.
Hi. Nice to meet you.
Nice to meet you too. Good morning, Fabrice.
Morning.
Good morning, Professor ICHISE.
So we start?
Yes, of course.
Okay, so I'm the president. So I welcome to all the members of the committee, and we start now your defense. You have 45 minutes for presenting your work, and then we move to the questions, first from the reviewers, and then from the examiner, and for myself, and also from your advisors.
Yes, I see it. Thank you. So,
Please, I give you the floor.
Yeah, thank you. So before that, I will check first whether the live streaming in YouTube is working right now.
Okay.
Yes, it seems everything is working.
And have you slides to share with us?
Yes, of course. Okay. It's clear for everyone? I will start right now.
Great.
Okay. Hello, everyone. Thank you very much today to attend my defense remotely from Zoom or from YouTube. My name is Ziwei XU, and I'm a PhD student at University of Nantes and working in Duke team, and I'm affiliated to the LSDN laboratories. So today I will talking about my thesis, Enhancing LDA for Ontology Learning. The slide will take for 45 minutes, so after introduction, we will mainly concentrate on the two contributions in details, and then I will conclude the work at the end. So let's start by the research background. So for humans, during our educations, we are trying to deal with amount of data and transform those data into knowledges by so many processes such as collecting, organizing, and even at the end of decision makings. And then we are trying to store those knowledges for the reuse purpose in the future. So during step, we see that we pay main attention to the knowledge management. And however, there are some issues about knowledge management. For example, we can use so many different terminologies or the different terms to describe the same knowledge, or we have using the different rules or methods to store the knowledge. And also, the knowledge cannot be generated automatically by the machine. So in the domain of computer science, which is related to machine learning, the data mining, and also ontology learning, we could solve these issues resort to ontology. And from the first definition here, ontology is a formal, explicit specification of a shared conceptualization. Also, others who defined ontology as a representational artifact comprising a taxonomy as proper part. And module ontology facilitated to alter the structures, such as remove, add, or reach target modules of an ontology. And here I provide an example at the bottom of this slide. In the examples, this ontology was composed by 5 modules, and each module was led by the core concept in the dark blue circles. And for each core concept, they are related by the taxonomic relations linked to the subconcept. And it is worth to mention that we can see that the taxonomy, it composes the main structures of the ontology. So next part, I will be talking about the literatures to learn an ontology. So on the left side of this finger, we can see that we provide the processes of constructing an ontology. It starts from terms. Terms will form concept. Concept could organized according to relations. And relations could formalization enriched by axioms. And on the right side, there is a related techniques that is trying to solve the subtypes in the left side. So we try to summarize them into 2 parts, the statistic-based techniques, which include clustering, co-occurrence analysis, term subsumption, and topics, and also the linguistic-based techniques, for example, the seed words, lexicosyntactic patterns, post-tagging, and dependency analysis. And during the whole processes, we are trying to focus on the concept formation in our sciences. The general manner to solve these issues could be divided in 2 parts: the supervised minors and unsupervised minors. If we are given an ontology, we could apply a classifier to assign terms to a concept, which is a typical supervised way. And for if a set of terms are organized into concept of ontology, it is a typical unsupervised way. However, there are so many drawbacks according to those minors. For example, for the supervised way, the classes need to be pruned in advance. Need to be defined in advance. And for the unsupervised minors, the concept of clusters perhaps are not clear or not predictable. And trying to solve the problem about the supervised minors, we are trying to apply the clustering techniques and also the topic models. And the topic model is a language model, and the topic model, we can see that it could automatically analyze data and to discover the distribution between words, topics, and documents. The general ways to using the topic model for clustering is listed here, that we could get the topic terms distributions. And also, we could fit them to the clustering algorithm, and then we could get the cluster of words by topics. And also here, we name it topical clusters. However, those kind of topical clusters cannot always have the satisfying result. For example, the quality of the topical clusters is in doubt. It means that we cannot ensure the quality of topical clusters. And the second point is the topical concepts are different with the concept of an ontology. It means that it will lead to the mismatching between topics and the concept of an ontology. And we would like to summarize our challenges and solutions in our sciences by answering this question: how to apply topic models for concept formation. We divided them into the different challenges. For the first challenge, it tried to solve the 2 issues. The first one is how to form the topical clusters, and we try to propose the LDA-based clustering strategy. And the second principal challenge is how to adapt topics to concept. We try to embed the prior knowledge to LDA. And during our exploration for the principal challenges, we also infrared with some set challenges I also listed here. So there are three sub-issues for the set challenges. The first one is how about the performance for common term clusters? And the second one is what are the influencing factors for those topic clusters? And also, how can we extract the taxonomic relations if we want to for the further explorations? And the solutions is on the right side. So here, I would like to move to the first contribution. The first contribution here was listed in this figure. On the left side, we provide the ontology learning cake and try to tag each subtask with different colors. And the contribution part will provide the main targets and with the corresponding colors. For example, in the contribution 1, it's composed of two main sub-contributions. For example, the term clustering framework and also the LDA-based term clustering strategies. So let's start from the common methods for term clustering in the first sub-contribution. So the common method could be summarized into two different scenarios. The first one is the typical scenarios. It includes typical clustering algorithms, and those algorithms will be used on the representations. And also the other scenarios, which include the clustering strategies. For example, they could use the entropy-based clustering strategies or based on the graphs. And however, we found that it does not exist a term clustering framework which try to formulate all the steps. So this leads to our first contribution. We are trying to formalize the typical clustering scenarios for term clustering framework. Since it lack of the structural presentations for the previous method, our task is become to clarify the necessary stages of typical clustering scenarios, and also try to explore the possibilities in different stages. For example, here, we provide 4 stages in the term clustering framework. It starts by corpus preprocessing, non-phrases representations, non-phrases clustering, and also evaluations. So let's start by the first stage. Here, we provide several techniques for preprocessing, such as post-tagging, dependency parsing, the extraction of n-grams, and also the extraction of non-phrases. So in the linguistic, we are trying to, based on these hypotheses, the nouns and the verbs compose the main structure of a sentence. So in the bottom of the figure, we are given this kind of sentence, and this sentence was tagged by post-tagging and also the dependency parsing. So from those informations, we could extract the noun phrases, which is abbreviated as NPs, and also verb preposition combinations, which is abbreviated as VPCs. And those extracted terms will play the main roles in the next reconstituted corpus. For the stage 2, it is going to generate the terms feature space from plain text. For example, we divided the types of term representation into 2 parts, the frequency-based and also prediction-based. For the frequency-based representations, it includes term document representation and the co-occurrence representation. For the term document representation, we can see the example here that we're given 2 documents, and the rows of the matrix here is about documents, the column is the vocabularies, and the cells and the value in cells is about the row counts of them. For the co-occurrence representation, for example, we give a sentence: the cat sat on the hat, and the dog ate the cat and the hat. When we set the window size equals to 2, and the rows will become the vocabulary, and the column is also the vocabulary, and the cells in that matrix will become the occurrence, the co-occurrence, that is for the terms that is in these fixed context windows. And on the right side, the example is about the word embedding representations. For example, we have a predict word using the previous sentence, dog. And the dog is in the position C in the vocabulary, and the window size equals to 2. So in the rows, we gave the neighbor words, and the column is the vocabulary, and the cells in this matrix is equals to 1 if the neighbor rows is equal to vocabulary. And those kind of, and in this way, each neighbor words have the vectors, and those vectors will combine together to try to predict the vectors of dog. So that the whole mechanisms of the word embedding representations. And in our thesis, we try to include those representations and combine them in the experiments part. So in the stage 3, it is try to cluster terms based on their feature representations. For example, here we provide 5 classical typical algorithms, and they are based on different attributes such as distance-based or message parsing or density-based or the high-dimensional data. And on the right side, we provide that whether those clustering algorithms need the number of clusters in advance. So if we want to compare those clustering performance, we are in front of 2 sub-issues. The first one is we need to fix the number of clusters at first before the comparison. And the second issue is how to evaluate the performance at the end. So let's give us the ideas for stage 4. Stage 4 is try to measure the clustering performance. We divided the indices into 2 sides. One is internal indices, and another one is external indices. The internal one is try to measure the compactness and the separateness of a cluster. It includes seed width weights and Young index. So we give example on the right side of there. It is the seed width weights. So we see that the seed width weights is try to measure the difference between the A, the average intra-cluster distance, and the B, the average inter-cluster distance. And for the external indices, we're trying to measure the coherence between the cluster labels and the assigned cluster classes of good standard. It includes asymmetric rank index, micro, macro, and pi-wise precisions, the Marshall correlation coefficients, and adjusted mutual information scores. So on the right side, we provide the examples of the calculation for micro-precision. For example, we have 3 clusters, and we have terms in that clusters. And of course, we vote for the most influence labels for that clusters. And then we try to calculate the correctness of the matching between the terms and the labels. And those portions of correctness is the micro-precisions at the right side. And so in summary, we try to formulate our term cluster framework in this graph. So it begins with the corpus preprocessing. By using the post-tagging or dependence parsing techniques, we could extract terms, and those terms will be used to constitute the corpus for the next step. And in the second stage, it includes the feature selection and the feature representation techniques. And then it is about clustering and the evaluation. And it is worth to mention that during our exploration in the term clustering framework, we also proposed a kind of representations. So before start, I will give an example. For example, in the left side here, when we are given a sentence, dog drink water and Zoe drink cola. If we try to form the normal nouns and verbs co-occurrence representations where the rows are nouns and the columns are verbs. So therefore, all of the 4 terms perhaps have similar vectors. But in our proposed representations, we are trying to distinguish the verbs with the different syntactic roles that they occur with. For example, we distinguish drink with subject roles and drink occurred with the object roles. And in these ways, the vectors of dog and Zoe become similar, and on the other part, the water and cola is much more similar to each other. And this kind of cluster is much more conform to the common sense for us. And on the right side is the overview of our proposed representations. And because of the representation is composed of the row counts, so we also proposed some variants about the proposed representations here. For example, we're using the TF-IDF techniques to generate the weighted co-occurrence representations. And also we use the NMF techniques to generate the condensed co-occurrence representations. So right now, we finished the introduction about the term clustering frameworks. So next step, we will try to introduce another sub-contributions here for the LDA-based clustering strategy. So the LDA is a typical topic model, which is named as latent Dirichlet allocation. Here on the left side, we provide the figure that is plotted by LDA-based tools with 30 topics. And here we saw that it has some problems. For the problem 1, a topic maybe contains too many general terms, which make the topic is not that significant. And problem 2 is some topics overlap with each other, and it kind of lead that the topic cluster need to be pruned. And at that time, we are not solving the problems about polysemy here. So let's go to the details about the problem. For the first problems, how to distinguish significant topical clusters. So at first, we need to define what is topical clusters. For us, we're trying to aggregating terms who have the highest probability of that topic. And a significant topical cluster is that the highest probability of the terms in this topic is far above 0. So we can see that the finger in the x-axis, we provide it is about 200 topics, and in the y-axis, it's about the topic words probabilities. And the black dot it is trying to indicate the values, the highest value, the top 1 values for that topic. And the end of the gray arrow is the top 5 values about that topic. So we see that we have 200 topics in total, but only 50 topics are significant in these graphs. So it means that it is really, so the terms show its important role that it could distinguish the topical terms with the normal, with topical cluster with the normal clusters. And let's go to the problem 2, is how to prune topical clusters. So we try to select the top n terms for each topical clusters. So we provide the figure here. On the left side, each topic clusters has top 20 terms, and on the right side, it has top 50 terms. And the dashed line here is the average values for those extraction terms. So we see that from right side, for the top 50 terms, it almost covers all range of the significant topic terms probabilities. So here we can conclude that the topic n could used as the pruning rules for the topical clusters. And here we provide the pseudocode of the clustering strategies. It has so many details, but I want to introduce here. We try to write this pseudocode into 3 parts. The first one is try to assign terms to topics that have the highest probability. And the second is try to solve the problem 1. That's to remove non-significant topic. And the third part is try to solve the problem 2, is try to reserve the top n for each topical clusters. So here, we have provide the comparison between the LDA before our clustering strategy and after our clustering strategies. On the right side, on the left side, that is all non-phrases without clustering strategies, and on the right side is the red zone non-phrases that is plotted by TSNE after clustering strategy. And we see that on the right side, the black dot is represent the non-phrases, and they are trying to compact each other and separate from the other clusters. And the red text annotated here is about the locations for core concept in computer science domain. And we also saw that they are evenly distributed, which is a quite welcoming outperform. And right now, I would like to introduce our preparation for the experiment. At first, it's about corpus. We're trying to focus two corpus, a router corpus and a computer science corpus. Router corpus is a collection of documents that appear on router newswires. And the computer science corpus include the abstract of the academic articles that are extracted from the Web of Science in computer science domain. And we provide some statistics here, which include the number of documents, number of tokens, and number of non-phrases and number of verbs. And in our experiment this time, we will focus on only on the sampling corpus because that the verbs, the number of verbs in the sampling is rather low, and which try to produce a lower dimension about our proposed representation, which is easier for our experiment. And here I would like to introduce our step to manually building the golden standards. The problem is that before continue the experiment, we found there's no benchmarks for term clusters on ontology learning. And we tried to label the clusters by multiple annotators in the first step. And then we try to measure the agreement between each part of the annotators. For example, we're using Cohen's kappa or the agreement scores. And then we obtain the golden standard for each corpus at the end. Let's see the statistics on the right side. It includes 4 corpus in routers, 4 core concepts in routers, and 11 core concepts in computer science. And let's introduce some experiment sightings before introduce more about experiment. So at first, it's the choice of key. The key is the number of topics. Or here is a number of clusters. So the key means key method and co-clustering algorithms. They have variable keys. So we set the keys in advance. And for the affinity propagation and the DB scan algorithms, they could choose the number of keys by themselves. And for all the result we provide later is about the average values for 10 repetitions. And the size of the term clusters for LDA-based clustering strategy is that only select top 10 words for each clusters. And for the classical clustering strategies, there's no limitations. And for the other detailed parameters, they are citing in the default sightings. And here is the result. It's the first result for the term clustering framework. So there's 2 fingers. Let's see the upper fingers. Upper fingers is about the feature representations. Let's see that regardless of the blue lines, we saw the other lines was indicated with the 5 different feature representations. The 3 first feature representations start by NPVPC. They're our proposed representation and the variance of our proposed representations. And for the W2V is about word embedding representations. The NP's LD is the topic embedding representations. And from the upper finger, we found that except for the blue lines, the brown lines is outperform the other feature representations. And we can conclude that the topic embedding matrix outperform the other feature representations. And on the bottom figure, it is about the clustering algorithms. So we also provide the 5 different clustering algorithms, except for the blue lines. We saw that the right lines, which is indicate co-clustering, is slightly outperform the others. And in total, we saw that the blue lines is also is always outperform the others. We can conclude that the LDA-based clustering strategy is significantly outperform the typical term clustering frameworks. For more details, I came to here. We try to compare the classic term clustering in framework and also the LDA-based clustering strategies. For example, in the x-axis, we have 5 different feature representations, and for the different colors and the different shapes is indicated for the different clusters. So each dot in these figures is one kind of combination for this framework, and the dotted lines is about the LD-based clustering strategy. On the left side, that is the best result for Ziwei weights, and on the right side is the best result that is present in micro precision. So we can see that from the left side, the LD-based clustering strategy achieved almost the similar performance as the k-means. And on the right side, the micro precision showed that the LD-based clustering significantly outperformed all the other clusters. And for the feature representations, we found that the non-phrases and its variants significantly outperform the other representations when we in the aspect of the whole combinations. And let's conclude for the first contribution. At first, we proposed to the classic clustering in the framework. The co-cluster algorithm perhaps to show the poor compactness and separateness of the cluster, but they have a rather high agreement to golden standard, which is showing that it has a high value in micro precision. And the topic inviting representations show that it has rather high micro precisions. And for the LD-based clustering strategies, we found that it achieved the significant high agreement to golden standard than the framework, and here we found that it is an interesting strategy for further explorations. So let's go to the next part for the contribution 2, which is focused on the LD-based clustering strategies. So we can see that from right side of this figure, we also divided the contribution into 2 parts. One is try to using the core concept, which is also prior knowledge for LDA, and the other side is try to discover the taxonomy relations by the previous techniques. So at first, I would like to introduce that how can we use LDA. The main direction is we want to embed the prior knowledge over LDA, and there's 2 methods to embed the knowledge on that. One is applying on algorithms, another one is applying on the documents. For the previous method, it includes seeded LD, Z-label LD, and labeled LD. For the previous 2 LD, we will introduce later. And for the application on the documents, we provide the examples like SAP LD, which the researchers try to duplicate the document if they found the document is quite similar to or quite necessary for one topic. And for the twice trained LD is we proposed in 2019 in an international conference, and this mental idea is try to train the LD in the first time and extract the only topic significant terms and focus on those terms. We reconstitute the corpus, and based on that corpus, we try to train LD in the second time. And it is also used for the clustering purpose. So let's start to talk more details about the LDA. LDA is a probabilist model that is based on the document collections. So at first, we assume that we generate topics at first before any documents, which is corresponding to the procedure 1, and the graphs is here, begin with beta. And then for each document, we try to sample the Dirichlet distribution of topics. and the graph will start from the alpha. And for each word in that document, we try to choose the topic from the distribution in procedure 2.1. And then we try to choose a word from the distributions in the previous type of the vocabulary. So that's the general idea for LDA. And for the Z-label LDA, we try to compare the LDA in the left side. We provide the preciseness of Z-label LDA in the right side. So we see that it has two conditions that is different. At first, if a word is recognized as the seed word, the topic distribution will be fixed. It means the hyper alpha does not work. And if the constraint is applied, it means the influence of the fixed topic distributions will be weakened into certain portions from 0% to 100%. And for the seeded LDA, it is rather more complex. It tries to embed the knowledge into two parts. One is in the topic term distribution. Another one is the document topic distribution. For the left side, if a word is recognized as a seed word, they will use the indicators X. And from the indicator X, they will assign with a higher probability to choose the seed topics and lower probability to choose the regular topics. And on the right side, for those documents where the seed words occurred, the topics related to the seed words have a higher probability to be assigned. That the difference from the normal LDA. And here we would like to introduce our contributions for this part. So here in our thesis, we try to use to embed prior knowledge over documents. So there's two techniques here. The first is a core concept replacement, which is tagged as approach 2. It is to find the keywords in the document and replace it by core concept. We saw the example here in the bottom of the table, the bottom of this figure. Approach 2 add the machine learning at the core concept, comparing to the approach 1, where the sub-vector machines was replaced. And for the next embedding technique, the subdomain knowledge supplementations, tagged as approach 3, which is used to add keywords of the document at the tail of this document. So we see the example that the compute in the rows of approach 3, the computer vision and yield prediction was added at the tail. And approach 4 is try to apply both of the techniques together, and we see the result is here. So that is our ideas to embed the prior knowledge in documents. And here I would like to introduce our prior knowledge resources. So core concept and keywords could all of them be used as seed words for algorithms like seeded LDA or Z-label LDA. And the core concept is defined by domain expert in advance. For example, machine learning is a core concept of computer science domain. And keywords is extracted from the extra information provided by the document. For example, we saw the document 1 is acknowledged to talk about k-means clustering algorithms. So on the right side, we provide the statistics for the keywords. So before we introduce the results of experiment, we would like to provide the introduction about the parameters for LDA. At first, we would like to vary the topics from 10 to 20 to 200, and we set alpha and beta to be default semantic distribution, and we also alter the other parameter trunk size from 10 to 200, and the result was provided with 10 times repetitions, and the target is that we try to find the optimal number of topics regarding to seaweed weights in computer science courses before we continue. And the result that the best options is shown to be 50 topics with a certain number of chunk size. So next experiment, we try to use the number of topics equal to 50. For the experiment 1, we're trying to focus on find the best treatments in documents aspects with 4 cases and 4 approaches. The 4 cases here is about the contents that we include in documents. For example, the first case, we only include non-phrases which appear in the different syntactic roles such as subject or object. And the second case is we include also the co-occurred verbs for that non-phrases. And the third case is we only include the non-phrases that exist in golden standard. And for the fourth case is that we only include the non-phrases that have high topical significance in the first training time. And it's also namely the cases twice trained LDA. And the result is shown in the bottom table. On the column, we provide 5 different metrics, and on the rows, we try to summarize whether they have preferences for those cases. And here we can see that for the 4 cases, only cases with golden standard try to outperform the others, but unfortunately, this kind of case is not generated for other, cannot be generalized to other experiments. And for the cases of approaches, we found that approach 4 outperform most of the occasions in the according to the metrics. So let's go details with this performance. So here I provide the results for micro, and pile-wise metrics. The x-axis about the cases combined with approaches. So we can see on the right side it's a checking table for what cases we mean and what approaches we use. So we see that when for the cases start with C1 and C2, they are the artificial documents, which is only include non-phrases in golden standard. They achieve the rather high score, but not generalized as we talked. For the case start with the case 3 and case 4, we found that the effect was little. It means that the non-phrases restriction, where it only includes syntactic rules such as subject or object, they have little effect for the result. And the best combination we discovered is the C6A4. C6 is that we include all the non-phrases and all the co-occurred verbs. A4 is that we use the proposed 2 approaches together. And let's go to the experiment 2. It's about the target. This experiment is trying to compare the optimal knowledge embeddings LDA and the Z-label ID and seeded LDA. So on the left figures is about the macro precision values for Z-label LDA. We can see that the code lines is indicate the results by the computer science corpus, and the warm lines, which is indicated by the Ryutaro corpus. So we can conclude in the left side that Z-label ID is quite sensitive to corpus, and it has a significant outperform the C6A4. And on the right side is the one for seeded L modules. And we see that most of the lines was quite decreasing along with the number of topics. We can conclude that it is sensitive to the number of topics. And the seeded models try to outperform normal LD, which is indicated here. In blue lines, and they slightly outperform C6A4 in some number of topics. And the knowledge embedding in algorithm is quite outperformed knowledge embedding in over the documents in our conclusion. So before we conclude, I would like to have a brief introduce about the taxonomy relation discoveries. And first, they could be achieved in two sides. One is internal side. We can extract the text in significant and statistic features in internal part, such as pattern matching, structural patterns, lexicosyntactic patterns, and non-modifier relations, and also the external part from the published taxonomies of the common knowledge bases. For example, from Freebase, DBpedia, Wikidata, and WordNet. And here we would like to introduce briefly how we use the predefined the previous work to extract the knowledge by ourselves. For example, we're using the pattern matchings for internal manners. We got the result that the formal query language is a query language. And in the external manners, we try to matching the terms in our corpus to DBpedia and Wikidata taxonomies by using the SQL languages. And in the external manners, we found that we acquire almost 200 relations. And for the hyponyms extraction in the internal manners, we found around 100 results. And those kind of relations will then contribute the end of our achievement. So on the upper side, it is the ontology that we introduced in the beginning of the slide. And in the end, it what we achieved at the end. So we can see that the term clusters appear to in this ontology. For more details, we also provide the result in the new 4Gs for the direct visualization. So here, at first, we provide the resulting ontology of computer science domain. And the orange node and the brown node, they indicate the core concept and the sub-core concept, and then and they construct the discovered taxonomies from the Wikidata. And then are the main structures about our ontology. And on the next part, we try to tag the isolated clusters, which means that those clusters cannot find any concept they related to or attached to in the taxonomies. And for the dependence clusters, it means that fortunately they include those kind of concepts that appear in that taxonomies. And here is a zoomed version for the data structure core concept. So we see here in the taxonomies, they are related by its relations, and for the clusters, they are related by cluster 2 relations. And also there are also some words that indicate that they are clustered to the hash tables. For example, the hierarchical data structures, the key value, and non-uniform distributions. And then let's try to conclude what we have concluded in our thesis. At first, we propose a term clustering framework to formalize the possibilities in different procedures. And then it's about LDA-based clustering strategies to try to cluster terms from the text. And also, we propose the prior knowledge embedding approaches to conform the cluster terms to the core concept in ontology. And at the end, we try to discover the taxonomic relations internally and externally. And also, there has so many work that we want to do in the future. At first, we would like to remove some non-significant terms in the clusters because we found that in our previous result, there are several terms that is not related. And also, we want to discover more useful relations for different end-use needs. And then we would like to extend our algorithms or strategies to the other knowledge-intense domains, such as medicines, educations, or laws. And here is several publications during my 3.5 PhD life. And yeah, it ends with some references at the end of the slide. Thanks for your attention.
Thank you. So now we are we have the times for questions.
Yes.
So as before, yes, it is needed. So what I said before is that we come for find the question will be from the reviewers, the two reviewers, and then we move to examinators and to myself and also to the advisors. And I have no particular criteria for selecting the two reviewers before, so I give the floor to Hedi KARRAY as the first one, if you want.
Okay, thank you. Thank you, Mr. President. Thank you, Ziwei, for your presentation. And thank you to, let's say, to take into account our comments about the manuscript in your presentation by providing more illustration, more examples. So it's very interesting. Also, let's say, to be honest, I was usually against ontology learning. So from my perspective, ontology should be developed by humans and then improved by ontology learning. And so I believe that it's support activity to improve and to populate ontology and so on. And since few years, I start to change my view and to see that it's really important to have such works in order to, let's say, to improve ontology engineering process, because handmade ontologies is very a big task and is very complicated. So having support from ontology learning is something very important. So that's why I like your topic, and it's a really very challenging topic. So the question is how machine learning can support ontology engineering. My first question about your work, which is, I was expecting more ontology in your work, because the feeling that I have is that your concerns is terms. And my first question is related to, let's say, to your topic title, which is enhancing LDA for term clustering, for ontology learning. Sorry. So my question is, if you entitle your dissertation enhancing LDA for term clustering, there is difference. And then related to that, when we talk about terms, and sometimes we are talking about concept, I would like to have your view about the difference between term and concept.
Yes, thank you. I quite understand that it is really a tough work to build ontology, because for the first question is about how to use machine learning for ontology learning. For what I understand for my 3 years life is that as you have talked, ontology is first should be constructed by humans, and based on this, I think machine learning is trying to assist the further exploration for ontology based on the human construct ontology. And it is also the main idea of my thesis, where I'm trying to, based on their taxonomies, and that taxonomy is already defined in some knowledge bases, and I try to include more terms related to the concept. And that is my answer for the first question. And the third question is about the term clustering stuff. So it means that I think from what you think is that enhancing LD for ontology learning perhaps turns to be a more general topic than what I have provided in my thesis, because my thesis is more focused on the term clustering. And your question is about how can I link the terms to concept in this way, if I want to entitle that the thesis in that way. For what I thinking is that at first I want to cluster terms, but for the result of the clusters, it is kind of black box. We have no idea that they are because of the similarity of linguistic or statistic or something else or the semantics. And when I try to use the model LDA, I can ensure that the clusters is about topics. So it is more about the semantic levels. And at that time, I try to link the topics to concepts that we can find in ontology. And so here I could use the topics at the bridge to link the terms to concept. That's the main idea on my thesis. And I know that I didn't achieve a rather perfect work to making the linkage because as I provide in the results of my clustering, the clusters could be isolated. And if they are isolated, it means they does not link to the ontology anymore, or at least in my hypothesis, they are not linked. And for the dependency clusters that I showed before, so in that clusters, it includes the concept of a taxonomy. So at that time, I try to link those clusters to the taxonomy. So I think perhaps that is my answer to your previous questions.
Thank you. Thank you for your clarification. So I will continue in this focus on ontology concepts and so on. So also, I don't know why you focus on ontology learning for modular ontologies. My question is, what is the difference if your contribution try to be applied for an ontology as a whole, not modules?
Can you repeat your questions? I quite have lost when you were mentioning the modular ontology.
Yeah, you are dealing with modular ontologies, right? So if you apply your contributions on an ontology without this notion of modularity, what is the difference? Do you think that your contribution makes sense if we deal with an ontology without this notion of modularity? What is the added value to this modularity with your approach, for example?
Yeah, that's really a deep question and also a big problem during my thesis. When I'm always trying to find the difference or for the modular ontology and the ontology that I used in my thesis here. Because I quite understand that the ontology that I used in my thesis is not a typical module ontology, or we cannot call that module ontology. That is just ontology that have the main structure as taxonomies. So my answer to your question is, what if I, regardless of the modularities, how can I contribute my thesis to the ontology? So my answer will rely on the taxonomies. Even without the modularities, we can also have the taxonomies. So I can use my method here. But the problem is that I build the term clusters and linked to the taxonomies. And at that step, the term clusters could be removed, and they could be changed if they include other words in the term clusters. So the method itself, it's kind of include the ideas as a modularity. But the drawbacks of my thesis is that I only focus on the taxonomic relations and my clusters, but without the other relations. So as you have said, I cannot call that it is modular ontology, but I'm quite using the idea from that.
Mm-hmm. So do you think let's say, you just mentioned this, each cluster can be considered as a module, right? Do you consider this?
Yes.
Yeah, and you just mentioned that clusters can move. I mean, there is change if you add more terms, and this is one of the big issues, as you mentioned, because in ontology engineering, the question is today, if we want to deal with modularity, how we can define those modules. And also ontology construction and building process is driven by specifications of the ontology. And usually we decide about modules according to the specification of the ontology. And one of my questions is how you can deal with ontology specifications to construct your clusters, and you drive your learning. I mean, if you have competency questions, for example, you have use cases about how the ontology will be used, the stories, how you can integrate all those aspects in your learning in order to build your clusters.
Yeah, I understand your question, because it is also what I concerned in my perspective, in my future work. Because as you mentioned, a main word is the specialarity of the ontology. And you also mentioned the user case, I think is also the problem right now. Because in academics, we are trying to produce the ontology in a general view. But in the user case, we're trying to, we prefer to build ontology in our own user needs. So the specialty of ontology is quite important when we are trying to use that in reality. And for the specialarity of the ontology, I think in my mind, I impose two ideas. The first idea is that whether this ontology is in a knowledge domain, or this ontology was special in the user case, such as the ontology try to search for the human resources in a company. That is different from the ontology that we talk. That is one. And the second is about the relations they want. Because right now in my thesis, I only focused on the cluster 2 relations and also the taxonomy relations. But in the general usage about ontology, they have many customized relations. And at that time, my work perhaps cannot directly work in that purpose, but my clusters could work as a recommendation for this kind of concept if they mentioned. And that's my answer.
I'm happy to hear that, because I mean, in the manuscript, I haven't this feeling that it's presented like this is the manner to do ontologies, and this we should. I mean, even when you mention ontology engineering, the whole process, and you mentioned, for example, methontology as a methodology, I didn't see the position of your work in this, let's say, this process of ontology building. And you give the feeling that this is the way to develop ontology. And as I said, and you said, that it's a part and this is a support for developing ontology, but it's also let's say it's drive us to another question. I mean, I try to ask let's say more generic and big issues today in ontology area and ontology engineering, which is there is, ontologies come from philosophy, and there is different schools, and one of the main issues today is pluralistic approach or monoistic approach, in the sense of there is one ontology, there is different representations of the knowledge in the same domain. So if we, let's say, if we adopt an approach that say, okay, we can have only one representation of the ontology of this domain, do you think that your approach can work in this sense, and you be sure that this is the right presentation of things, and this is the truth, let's say? And from the other side, as we discussed just before. You say that clusters are moving and we can have different representations.
Okay.
So, yeah.
Thank you. I quite understand, and I got some inspired from what you said, that ontology is based on philosophies. And the question first is about whether we can have one ontology to explain one domain or the knowledge in that one domain. I thought yes, we could. And we have so many knowledge bases available right now in the network, and they give our structures about for each subdomain or sub-knowledge. I think in the philosophy perspective, my answer is yes. And for the second question is, how can I use my clusters? Because the cluster path will move to serve for this purpose. My answer was that it is not sufficient right now, but as I said, it can only work as a recommendation sometimes. So for the specific purpose use, my method could work as a supportive, but the main part or the main ideas is from the structure in philosophies. And yes, I think my functions in general was supportive.
Mm-hmm. So another related question. I don't know, Mr. President, if I have more time to ask more questions.
Normally, I don't know, you don't have a limit in some sense. But yes, what is
I will not abuse.
what is planned is to stop at 1 o'clock, but it's much better that we talk about Fabrice.
Okay, right. So I will try to be brief in my questions. But I think the main idea is to exchange, and it's not, let's say, hard questions, but I would like to discuss. This is my objective. So when talking about philosophy and so on, I was wondering, when you use core concepts and so on. So there is a big movements now and direction to use top-level ontologies coming from philosophy to develop ontology and drive domain ontologies. So those ontologies are domain independent. Okay, if you take the example of basic formal ontology, for example, talk about occurrent process, material entity. So such kind of core concepts for top-level ontologies, do you think that can be used in your approach to drive the ontology construction later, and to say, for example, this cluster can be classified under, I don't know, this concept in this top-level ontology?
I quite understand, because as I understand well, the ontology you proposed, that when we are using some methods or some techniques as the core concept for the top level ontology, and how can I use my method into there. And for me, I think for the model that I use is the topic models, and they are more about the concept. And that is try to measure the occurrence between words, topics, and documents. And I right now, for my own opinion, I don't think topic model, this kind of language model, could deal with the higher concept in philosophies, such as when the core concept is about technology. It means we need to include about the technology for any kind of domain. So in this way, I think it's quite difficult for me. And I think perhaps it's another direction, and that direction is that I need to learn more. So I cannot give you answer, but I can ensure that that my thesis here is quite different from the ontology that you cite. Mine is domain dependent. because of the nature of talking model I use. So that's my answer.
Thank you. Yeah, as you said, it's your approach. That's why I would like to see what is your opinion as perspectives, and how we can relate those topical clusters and domain dependent with higher level of domain independent. So this is a big question also to link this, because as I said, I mean, even with handmade ontology is not easy to do it, to relate domain aspects to a high level abstraction from philosophy and domain independent classes and concepts. Also, one of the questions is, how do you deal with, in your text, between a concept and an instance? Because you are using terms. How you make the difference to say and to decide, in my ontology, this is a class and this is an instance?
In fact, in my thesis right now, I didn't make a distinguish between instance and concept. But there is a interesting result in my clustering is that most of the clusters that I used to extract for a cluster at the end was the instance, and seldom of them was the concept, except for the core concept, because they have a really high influence for the whole documents. And the concept is quite, I think, because of the algorithms for talk models, and because of the algorithms at first when I filter out some words, the instance try to stand out from the concept because they are more specific and they can show out their significance in the topic models. So, so that is in my work. But in my opinion, I thought in the clustering algorithm that I used cannot distinguish these two, but the taxonomy that I use, they could give me ideas. That is definitely a concept. And the clusters that I try to link that to the concept in the taxonomies, I can say that it includes concept and instance as well.
Okay, right. So let me give you an example.
Yes, please.
If I say apple, if I say blackberry, kiwi, orange, mango, can we cluster all those terms?
Yes.
Okay, what is the topic of this cluster?
Is the topic in my thesis does not have label, but I can see that it is linked to fruits. And if in my method, this kind of cluster will link to the domain of fruit or the specific fruits in the branches of that, such as a fruit for human to eat, like this.
Okay, I was talking about brands.
Branches?
Brand. No.
Brand.
Apple is a computer, BlackBerry is a phone. No, this is what I call, this is the semantic and the context. And I think, yeah, you should drive also your topic. I think because your let's say your corpus is already driven and you know which domain you are dealing with. So there is no problem. But if you take it as general, this is one of the big issues that what we call, maybe you call it topic, but it's the context. Even in the same context, I mean, if I go to shop to do some shopping in a big supermarket, if I say apple, blackberry, kiwi, mango, it's really fuzzy and we don't know about what we are talking. So let's say to conclude, I have two quick questions. In slide 41, you present a modular ontology I didn't well understand if this is the outcome of your algorithm or it's an example. The ontology that you provide in slide 41.
41. I will check.
Yeah.
41. This is an example.
Is an example. It's
Yes.
not the outcome of your algorithm.
Yes, it's not. This is the outcomes of the algorithms. I
But
visualize them in Neo4j.
This is the clusters and not the ontology, right?
Yes, they are not included in the ontology here.
Okay, that's great. My final question is really a general one.
Yes.
Did you develop ontology by hand?
In fact, no.
Did you use Protege to say, okay, I have this domain and I develop an ontology just to try?
No, because at first when I use Protege is with a really typical example as pizza. We have different pizza and we try to split it. And for what I understand from that tutorial is about taxonomic relations. And the result I got at the end was clusters. So at first I didn't use proteges to try to write down or link my ontology. But at the end,
ontology. I mean, you are dealing with a very nice topic. And one of the arguments is that ontology construction is complicated. And if you don't try to do it, and you take any example and you try to develop an ontology and you test by your hands the complexity of the process, you can be more convincing when you defend ontology learning. That's why I ask this question. It's good that when you talk about the importance of ontology learning and how you classify or the position of your work in ontology engineering, if you already did this and we talk about your experience and you have a background on that. Okay?
I see that. It's a good advice. Thank you.
That's all for me. Thank you, Mr. President. Thank you, Ziwei.
Thank you.
Giuseppe, your mic is off.
Sorry, we can move to the second reviewer, Julien Versin.
That's me.
Yeah.
Thank you, Mr. President. Thank you, Ziwei, for your talk. Thank you, of course, to Fabrice, Mounira, all the people that invited me to this defense. I appreciated the talk, and in particular the illustrations you gave during your talk in order to support your research. I'm not an expert of ontology learning, but I know something about that, and I know in particular that it's a difficult, long-standing topic in the research in ontology, in knowledge engineering, and so on. And I guess it's not a problem that is already solved totally. But I think it's not obvious to propose a new contribution in that area, and it's what you try to do. You're a courageous woman, so it's a good point. So I have some remarks to begin with, and maybe precise questions, maybe technical questions, and after that I will ask more general questions if you like.
Yes.
So first of all, about my remarks, fundamentally it's a difficult problem, in particular because we know that human beings, we don't have the same way to categorize, to organize our knowledge. And when you are faced to a problem, we know that some people will use some concepts for solving this problem, and other people will use other concepts, and maybe at different levels, maybe more precise concepts because you are an expert, and more general concept when you are not an expert. So the difficulty is that we have different views, and it's very difficult to find core concepts all the people will agree with. So fundamentally, it's difficult, at least for that reason. So this is maybe the difficulty you were faced to during your thesis. And this is maybe the reason why when you ask, you want people to annotate and to evaluate your concepts, you found that it's the agreement between the annotators were very, very low. And at the end, you just use one annotator because of that reason, I guess. And it's I can give you other examples because I work in a university of social sciences, humanities, and regularly I have projects with people in social science, in geography, and so on. And one thing they try to do is to categorize textual information into predefined categories. And for them it's very difficult. When you are working with one people, it's possible, but when you are working with 2 people or 3 people in political science, let's say, they quickly they disagree with the categories themselves. So it's very difficult to build a machine learning system in order to place the text into these categories. So I know this problem, and this is the reason why building a fully automated system for me it's a dream. I think. I guess the solution is to not to build one ontology with one set of core concepts, but maybe to trying to build several different ways to categorize the concepts. But this is a difficult problem, of course. So this is just my first remark. So I will switch to my questions now. So as I said, I will begin with more technical questions. It turns out that since a long time ago, but recently, there is maybe a domain. I don't know. It's a domain, but you have this conference on representation learning. So representation learning has become a major conference in AI and machine learning. And the point is, it's not new, but it's to find automated ways to find a good representation of the data before doing further processing, such as classification, clustering, and so on. So the main point is to find a space in which you can embed your data so that you can solve downstream tasks. It's a representation learning. And when I read your manuscript and again the presentation, I found that maybe sometimes you are a little bit confused because for instance, you distinguish on one side techniques such as LDA, and on the other side, projection techniques such as NMF or SVD. SVD is just a generalization of the classic spectral decomposition. So all these techniques can represent an object such as a document or a word in a space. For instance, for LDA, you can have the word in the space of topics, okay? Or you can use a co-occurrence information to have a word in the space of words. Or you can use word embedding techniques such as word2vec in order to build this vector to represent, to describe your word. So from my point of view, all these different techniques are all the same. They are building a space in which you can describe your word, and after that, if you like, you can do clustering on top of that in order to extract clusters of words and maybe concepts. So this is my first question. What do you think about that? Are you still sure that you can distinguish on the one side topic modeling techniques and on the other side embedding techniques?
Thanks for your questions. As I reformulate your question is about as I summarize, there's two different representations. One is about the topic embedding, and another one is word embedding. How can I distinguish them from each other? And
not exactly. Here you say that you have two types of embedding, but in your manuscript and when I hear you, it wasn't that clear. Meaning that on one side it seems that you have the clustering or topic modeling techniques, and on the other side the projection embedding techniques. On my side, or from my point of view, all this can be under the same umbrella, you know.
I understand. I agree with you that for most of the representation learning, they are trying to just build up the space, the feature space, and that feature space, once they have built up that, it is they are the same. They are under the same umbrella, and for me, and the difference for between the topics and word embedding is that for the topics and embedding that we use is word2vec. We try to compare them with 5 different clustering, and we found that the topic embedding is try to outperform the word embeddings. And at that side, we found that is interesting. So based on the topic embedding, as you have already said that for each features on the topic embedding, they could already be seen at the theme, at the topic already. So at that time, the topic embedding itself, it could be used as a clustering at the end if we define a certain rules about the clustering. But for word embedding, that is difficult for them to consider one feature about embedding as a topic or as some meaning related to concepts that it exists in our common sense, because they are still black box for us. And that is my answer.
I see. However, in your manuscript, I didn't see any mention to previous work that tries to combine word embedding techniques and topic modeling. Meaning, I know at least 20 papers in which they try to combine both techniques. Are you aware of this kind of literature?
Can you repeat that?
The literature that try to combine both information, meaning I have a model, for instance, in which I can use word embedding vectors, but also in the same time you have a mechanism similar to LDA. So you combine both both way of seeing the problem. I don't know how to explain.
I think I try to divide them into 2 contributions. For the first contribution, I try to focus on the representations, such as topic embedding representations, and that is the result from LDA as well. And on the second contribution, I try to use this kind of embedding as a clustering strategy.
So, I understand that.
Yeah.
No. What I said is that in the literature, you know, you can find other people who worked on how to combine word embedding and topic modeling in the same model.
Oh, yes. I also proposed that there's one algorithm that is called topic2vec.
Yes, it's one among 20 or 30 of them. Okay.
Yes, and I even tried to. I read this paper for several days, and I even tried to use their code to get the result. And the problem is the code has some problem when they're provided. Is I failed to implement them at the end. And but from my experience, I know that there are so many works try to combine word embedding and the topic models with each other. Perhaps they are trying using the topic embeddings and embed into the word embeddings and then combine them together. But for me, at the end, all of the embeddings we got at the end is the It's also the black box at that side. So the features of that one cannot be
it's a magic,
considered as topics.
It's a magic word to say that all these techniques are black box or we can ignore them, but okay. It's an easy argument.
I'm sorry. Yeah, this is my direct understanding for that.
Okay. That's okay for me. Okay, so I have a lot of questions, but I will restrain myself. Another question is related to yeah, it's related to the previous one. In word embedding, you can one main strength is to use pre-computed embeddings, meaning that you can pre-compute word embeddings, the meaning of words, based on a very huge corpus, such as Wikipedia, Google News, blah, blah, blah. And you leverage this information, rich information, into your own solution. And did you try this? And if not, why?
Yes, for the pre-trained language models such as Transformer, as you mentioned before.
No. It's another question that will come later. Okay. No, it's not the question. No, it's easier than that. It's just you have just a bunch of vectors that encode the semantics of words. Mm-hmm. And did you use this kind of information?
In my thesis, I didn't use the predefined models or this kind of information because I'm focusing on the noun phrases. So it is the 2 or 3 tokens combined together. Yeah. And at that time, it's difficult to use this kind of model. They are based on tokens.
Okay. We can find a trick such as, taking the inertia center of the 2 vectors and so on, but okay.
And try to add them together or to get the average. Yeah, I tried this, but I found the result was not that satisfying.
Okay. So switch to the third question is related to polysemy, because I found that in your manuscript you evacuated very easily this aspect, saying, okay, I will consider that I'm focusing on core concepts, so I can use a crisp clustering in which I put one word into exactly one cluster, and that's it. However, it's clear that some words are polysemic, so that they can be placed into several clusters. So this is a difficulty I found in your work. Why do you think your assumption is strong? Why do you think it's possible to get rid of these polysemic words?
In fact, in reality, I know that the polysemy also always exists in any kind of language. And the models that I mentioned that I wrote in my thesis, some models such as LSI or LSA, they cannot solve the polysemy efficiently. And yes, I need to apologize that is not a correct or scientific writing way to say this. I will correct later because at that time, I think I kind of don't have a clear view about how they work for the polysemies. And the reason that why I get rid of to include the polysemies into my clusters is because my hypothesis was simply based on the cluster that they don't have overlapping. Because I saw the overlapping in the cluster will induce the redundance of my ontology at the end. And that is the main reasons.
But the reason is driven by the choice of your clustering algorithm, because you don't want overlapping clustering. So at the end, you favor clusters, non-polysemic words.
In fact, I quite understand you, and that is the main idea. But because let's go back to the model that I use is the LDA, is the topic models. And in that topic models, my defined clustering strategy is whether this word is significant, contribute to this topic. And if they are not significant to contribute to the topic, I will not select them for the cluster at the end. And for some polysemies, they will contribute to 2, 3, or even 4 topics. At that time, their probabilities to the topics at that was distributed, so the value was quite low. So that's why at the end I try to exclude the synonyms terms at the end. It is also because of the clustering strategy that I defined based on the topic models.
So even with LDA, for one given word, you attribute it only to one topic only. Even so, it is well present in several topics.
Can you repeat it?
Let's take one word,
yes.
Avocado, or whatever, something.
Yes, yes.
Maybe it is, it has a high likelihood in 2 topics, let's say. I don't know, 60%, I don't know, whatever. But at the end, you choose only one topic for this word?
Yes, I think they have 3 options. The first one is if it has a rather high probability in one of the topic. Oh, no, sorry, I will came back. So if we have avocado and it have a quite high probability to 2 topics, at first we will assign it to the highest topic that it belongs to. And the second step is we need to ranking all the words in the topic the avocado belongs to. For example, as I talk, we can select the top 10 or top 50 or even top 20.
Okay, but one word will be in only one cluster. It's your main assumption is this work. Okay.
Yes, and
okay. I don't know. I'm not sure it's a very reasonable assumption. Okay. And so it leads me to the other question. It's a BERT question. I have to ask one. So you certainly know that there is a tremendous work in NLP these last years related to contextualized word embeddings, meaning you can have not only one vector associated to one word, but possibly several ones because they will be contextualized depending on the surrounding of the word. It's the transformer, and after that, BERT, GPT, and so on. What's your feeling about this? Do you think it's possible to leverage this kind of work to your own work?
At first, I want to indicate that I was not really familiar with the contextual word embedding. I tried to use the BERT, the predefined language model BERT, to use as a word embedding matrix in my thesis. And at that time, I found because they provide different vectors from their context, so they have so many dimensions for only one word. As I found, what I found is in my BERT is they have 300 multiplied by 200 and 200. These kind of dimensions just for one word. At first, I want to try that. At least I try a really small corpus and try to get the word embedding at the end to train it whether the cluster was good or not. But during my weak management on coding, or because of the capabilities of my computer, I failed to deal with this high dimension. So I think the problem is that first, perhaps I don't have the enough background to deal with the high dimensions. The second is, if I want to reduce the dimensions, is whether it has some influence for the result regarding to the dimension techniques that I used on that. So I didn't consider the contextual word embedding at the end of my thesis.
I understand. Yeah. Okay, thank you. I have at least 2 questions now. One, it's a multiple question related to your experimental framework, and another one is a more fundamental open question at the end. On the experimental part of your work, I have several questions, but I will give you all at once. The first is why not using word similarity datasets? Because there exist multiple datasets where you have synonym groups, groups of synonym words that has been annotated by people. It's a word similarity. You can find many of them. This is the first question. The second one is I didn't understand why you evacuated the topic coherence measure. From my point of view, it's a good measure, maybe not the only one, but a good measure in order to assess whether a group of words are well connected together in terms of semantics. And the last question related to experimental, it's related to data. You worked only on well-written corpora such as newspapers and maybe scientific articles, but it's a very well-written text. What about more complicated text such as, I don't know, from the social media or chats or less well-written text?
Okay. So the first question is about whether I don't use some data sets that have already tagged some similar words. In fact, I have found so many data sets, but they are not in the plain text format. That is my shortage, I think. And for other data sets, they have word similarity, and then at the end, I think for me is that they provide the word similarity. They cannot provide me a support to evaluate my result at the end, because my result is about term clusters, and the similarity perhaps at that time, I have my shortage about the measurement, whether I can use that the words they are similar, so they can use as the one metrics to measure or to check the quality of the term clusters. And the main problem is that I didn't find those kind of data sets. I have think about this kind of data set before, but for the plain text data set, they are more about the document clustering. So they provide that whether this document is about the same topic or not. And there's lots of the documents that is talking about focus on the terms. Perhaps word similar data set could be a good resources for my next step. And for the second question is about why I didn't use the topic co-occurrence matrix to evaluate
topic coherence. And maybe using an external corpus. You know, you can, for instance, you have three words, and you can compute their coherence based on Wikipedia and so on, so that you check whether these words are usually used together in the same context.
Oh, yes, I quite understand, because I also read a paper is about the topic coherence, right? And one topic is trying to using the Microsoft concept, and the Microsoft concept, this kind of database, they have already provided the values to give the metric, to give the values as whether they thought these two words is similar. And those micro concepts, this kind of data sets, or we call it is graph, they are based on a big number of corpus. This could be a really convinced sources if we try to use the coherence to measure the topics, to measure the coherence between the terms. But during my experiment of my thesis, I don't I didn't get touch with this kind of evaluations until that at the third year, almost at the end of the thesis. I found that in the model that I used, it is called Ginsum, and they provide the interface. It is also called coherence models to give the values at the end. But at that time, my experiments has already finished, and so I didn't provide the values at the end. But I quite include a small chapters to introduce this kind of metrics.
I see. And there is a Palmetto library in Rudder, I guess. Okay, but in Gensima as well. Okay, thank you. And the very last question, I promise, is maybe a more difficult and fundamental one. It's related to your very assumption, meaning when you would like to build categories, you have different ways, different philosophy of doing this. When you go back to the Greeks, with Aristotle and so on, you have the necessary and sufficient conditions in which you place an object into a category where when it checks a set of features. For instance, a dog, it's a dog because it has a tile and it barks and so on and so forth. And this is exactly this. Your object has to fulfill a set of conditions. This is sufficient and necessary conditions. And on the other side, you have other theories developed, for instance, at Berkeley by Elena Roche on the concept of prototype. And for instance, K-means and such algorithms are based on this idea, meaning that you have a central prototype that is a typical example of your category, and you have less typical objects, and you have a degree of typicality between the objects. And you can have objects that are in between categories. So it's more fuzzy than the CNS. And necessary and sufficient conditions are more logical view of the problem. So you have these two ways to view the construction of categories. And I feel that in your work, you would like to combine both, meaning that on one side, you would like to build ontologies in which you have well-defined concepts, crisp clusters with a set of limited words and so on. And at the end, your instances will be associated to this concept or this other concept and so on. So it's a more NSC view, logical view. And for doing so, you use topic models that is at the end something similar to clustering. And you take LDA, and at the end you use heuristics in order to do clustering. But prototypical based clustering with similarities and so on. And I have the feeling that somehow it's somehow contradictory. So you would like to achieve some aim, but using maybe not the good tool. I don't know. What's your feeling about that?
It's quite a long and in fact, I didn't get so many things about the contradictory between that. So can you explain again? I know it is quite long. Perhaps give me an example.
It's long. But to sum up, in your work, the idea is to define well-separated clusters, well-separated concepts, but you use techniques fundamentally that are more smooth, that allow an object to belong to several topics. For instance, a text can belong to several topics, with a degree of belonging. And for me, it's almost contradictory. You have belong or not in the logical part, and on the other part, you belong more or less.
I see. Thanks to point out this question, because I didn't think about this problem before. In a logical way, seems like it is a bit contradictory before what I said cluster at the end, because I want they are well separated from each other, and at the end I try to link them in together if they exist in the same taxonomies. And I think at first it is quite difficult, but I want to reflect back to one example in my slide. I give the comparison about the LDA-based clustering strategy. So I gave two figures I will show here. I gave two figures. Yes, here. On the left side, I said that they are not really separate with each other. On the right side, I said that that is a good result, that what we want. Except for the separate clusters that is indicated by the blue dot, I also indicate the red text, and the red text is core concept. So at that time, I also consider that the core concept will not combine them to each other, and I anticipate that the core concept is also evenly distributed. So in the first step of this, the clustering, even though I try to encourage them to be separate each other, but I also care about that whether the core concept or the main ideas inside them exist, and also that they are kind of separate with each other. So at the end, when we are trying to link those clusters to the concept that we indicate here, I think it's more about the idea or the understanding between machines and humans, because machines thought they are different, but humans thought they are related, or at least they are partially related, such as some clusters is related to that cluster in the common sense for humans, but for the machines, perhaps they are far from each other, or they are not that related in the space. And also, I want to mention that on the right side, this is the two dimensions about the difference between each other. So, in fact, directly, we know that it is separate from each other, but we are not sure their similarity between each other, because it depends on different similarity measurement. So I thought that is not contradictory, because I am trying to use the machine first to set up the feature space, and then at the end, for the point of view of humans, how we can link them to each other, respect or regardless of the feature.
I understood the question, your answer. Thank you very much, Ziwei. I have so many questions, but I will stop here. Thank you again, and I yield you the floor, Mr. President.
Thank you so much.
Thank you. So we move to the examinators. So the first one is the examinator, which is who is the invited one for Japan. So yes. Mr. Ryutaro ICHISE. I don't know if my pronunciation is right, but please.
Okay, thank you very much for your presentation. I have several questions about your research, but maybe it's better to start from the detail of your research work. And I have a question about the page 25, in the experimental result. And so according to your report, even we increase the number of clusters, almost we can get almost the same result. And so Usually, if we increase the number of clusters, problem will be harder, and so that I have no idea about why that this is so stable. And so, do you have any idea about it?
Can I precise your question? Is why when I increase the number of clusters and the performance is growing according to the micro precision? It's like
Yes. So, do you know the some reasons for it?
I think, yes, I could explain it by the metrics we use here. So we see that from the left side of the finger, we do the micro precision. And the micro precision I provide example in previous slide is here on the right bottom side. So the micro precision, before I introduce micro precision, I want to make a distinguish between clustering and classification. For classification, if we have one term and we know that this classes is belong to one label, and if that terms have different label for the label of that cluster, we count it as 0 or we count it as false. But in clusters, the nature of the cluster is that we don't have a label for that cluster at first. So when we are calculating the macro precision, we try to vote the labels of the cluster before we calculate. And the vote of the cluster, we can see that on the third column is the most influencing labels. So they are trying to decide these labels with the majority of the terms. So in this way, this kind of spatial mechanisms that is different from classifications. When the number of clusters increase and the number of the terms in cluster will decrease, so the majority influencing labels will have a high proportions when the cluster becomes smaller. So that's why at the end of the results, such as in 25 slides, they're increasing slightly.
Oh, okay, I see. Okay, so my next question is about why the LDA is better than the others, and so what kind of characteristics contribute to this problem? So I mean that the LDA has several characteristics, and so what is the important point of the LDA for this problem?
I see. Thanks for your question. So at first, LD is a typical topic models, and the idea behind topic models is to try to find the kind of hidden topics among the documents, and they are trying to using the statistics about the words in documents and also the documents to try to discover the topics at the end. And why the topic model will try to outperform the others for me is that it is I think for me it depends on the usage. If we want to cluster those terms, and our golden standard is also made by the concept by the topics. So at that time, those kind of clusters was quite agree with the golden standard we build. And also for the golden standard is a correct one. And when they are using the other models, such as some clustering models, the result was not that good. Is because those kind of cluster results, perhaps they cannot combine the words together when they have a similar sense. Perhaps they have other similar features, such as appear with a same sentence or appear with certain verbs together. And those kind of features cannot make them to have a topic agreements for them. And another thing I want to mention is why I use topic models, because I found for any kind of text informations, we could apply them with topic models, such as some Twitter information, because one we can consider that one account, when they posted in one time, they could be recorded as one document, or all the tweets about one account we can consider as a document. So at that time, the topic model was quite efficient, and also topic model is quite interesting in that it can also trace the change, the alter of the topics along times when the time changes. So when the documents appear in different years, we can see the change of documents. And also there's another kind of mechanisms about LDA. It is about they are using the tempo informations. So I think topic model or LDA was a kind of a really worthy domain when we are dealing with all the plain text.
Okay. Also, you evaluate your idea with the several experiments. I'm wondering whether this difference of the methods contribute to the actual ontology learning or not. And so in your experimental results, the several method has the few percent difference. And so I'm not quite sure that it is affect to the real ontology or not. And so did you already investigate about the actual result, whether it affect the ontologies or not?
I understand your question. It is more about whether I can use my thesis or my methods on the real ontology. Because the real ontology for me is rather complex. So so in the start point of my thesis, I focus on the taxonomies. So there's only include one relations is a relations, and I try to manage the term clusters to those ontologies. But for the other ontologies, I think my method could be useful when it is related to the kind of one domain, or it is related to the structures about knowledge. But as I have discussed with Professor KARRAY, he also mentioned that for the other different ontologies, such as top-level ontologies, when it is more about the techniques or the methods, they are not related to domain anymore. It is not sufficient at that time to use topic models, but I think we could use other models. So at that time, if we want to enrich that kind of ontology, I think it is more related to the domain about relation discovery. Because once we are given an ontology, it means that most of the relations has already defined. And what for us is try to enrich the defined ontology. And if we have more time or we have more ambitions, we could generate more interesting relations by ourselves at the end to satisfy the different user needs. And yes, that is my answer. So in summary is my thesis is not sufficient, and for to use the user cases in one kind of specific user cases. And it also have limitations because the usage of topic models. But I think the main idea is we have learned that how to enrich the ontologies. And for any given ontologies, we can use these ideas to enrich it, or also to discover the other relations.
Okay, I'd like to clarify the difference between the term clustering problem and the ontology learning problem. And so in your thesis, the title is Enhanced LDA for Ontology Learning. And so but your main part is the term clustering, and also the so I'd like to know the difference between the ontology learning and the term clustering, which you mainly work, and also the missing point for the ontology learning. And so could you explain about it?
Yes. In fact, from the title, we see that ontology learning could be our final goals. And ontology learning, in fact, it is really large, and it includes so many technologies, and it includes also so many subtexts. And our subtext in the thesis was majors on the concept formation, from the synonym identification to concept formation. This kind of bottom 3 layers in the ontology learning data cake proposed by Ryutaro. Yes. And so the term clustering for us is one step, that is reaching the goals of ontology learning at the end. And this step, the target that we have achieved right now is try to enrich the taxonomies inside the ontology. So they cannot solve all of the problems to learn a general, a complex, and a sophisticated ontology. That is not really, and that is not really our target. And in fact, we cannot reach this kind of goals. In fact, because I think this kind of research problem perhaps also deserve decades of years for more explorations. And I think the last questions for you is about the limitations. I forget, it's limitations about the term clustering, or the limitations about other things.
Maybe the missing point to the creating the ontologies.
Yes. During my construction step for ontology, I found there are so many missing points. The first one is except for the taxonomic relations, what kind of relations I can get. And the other thing is that whether I can also combine the idea from the top level ontology to my domain related ontology. For example, for one concept, I can add more attributes about one concept. For example, if we give a concept such as machine learning, we could add attributes that perhaps whether it's a popular topic, or whether or what kind of domains it is used right now, and what kind of typical or the most popular models that people recently use, this kind of attributes. But this kind of idea is borrowed from the top level ontology. So there are so many missing points, and that missing point is kind of depends on what we want at the end. It means what kind of users need at the end.
See, my final question is about the generality of your idea. And so, although you tested with the several data set, maybe this obtained result could be changed depending on the number of the documents or the number of maybe the sets of the documents. And so do you think that do you have ever think about the applicable conditions for your idea to create the taxonomies?
I do agree. So at first, in the selection of corpus, at first of my thesis, I try to focus on some knowledge-intensive domains, such as computer science, and also some news, and where this news will mention so many concepts, and I would like to cluster those concepts later. And that is one. Another one is about the number of documents, as you mentioned, because the number of documents that I could resolve right now is about 10,000 documents, and I found that when I try use some subtypes about that, such as when I sample 1,000 documents. The result is that some topics perhaps cannot turn to be significant when I using a smaller data size. When I using a larger data size, it includes more concrete concept or smaller concept, and also the main concept is still large in the whole portions. So I do think this kind of range about the corpus influence our results. And
so
yes.
when you apply your idea to the actual domains, do you have any suggestions or for the how to collect the documents, or how many documents are necessary, or?
I think I don't have, I cannot give some advice about how many documents was necessary for if using my methodologies in my thesis. But I could give a restriction about the usage of my thesis is I prefer those kind of knowledge-intense domain to use this kind of thesis because at first the taxonomy was clear for that kind of knowledge-intense domain. And for the other concerns, I didn't think more about this right now. I'm sorry.
Okay, maybe you developed new ideas, but if we apply this idea to the other domains, that we need to have some knowledge about how to apply your idea to the new domains. And so if you also have some suggestions for this kind of knowledge, then it will be very helpful for the others. Okay, thank you very much.
I see it. Thank you so much.
Thank you. So it is my turn. So first, I I made some remarks on your presentations, and then I moved to some questions. Try to keep the question very short. So about the presentation, so I probably the only one that is not really aware of your work in this committee. So my view is maybe different from the other ones. I found a little bit difficult to follow your presentation because there are no examples, not clear examples to some extent, and it's or maybe an example that you follow till the end of the presentation that may be explained in deep details from an audience which is not aware from your work, the work itself. So there are plenty of things that you have done, but these things are a little bit presented in a difficult way from, again, the audience that is not aware of your work. And so so my question, then my question may be to some extent, have some trivial aspects because yes, I have no completely understood what your contribution in days, and so I move to the questions, and especially so I have to follow the slides because otherwise. Yes, so the question about the general process that you provide and that you suggest for learning ontology, and the process is presented as slide 8, so in which you suggest to find to follow some term clusterings, and then to move to some again adaptation plus some discovery of relationships that the whole process to some extent. So the first, I have not really understand the contribution number 1 because first in the LDA it seems to me that you have to know some kind of topics, so you have to know a priori these kind of things. So you have to list these kind of things that maybe it is unknown for any document, because let's imagine that you have a new ontology that you have built. So you have the set of subjects which are unknown, maybe. So you have to expect to provide these kind of things. And then you made some clustering around on that. And the clustering itself is something that is very known. So you made some clustering on terms, which is very known. And you have used also the term of terms in this presentation, in these slides, and then in other slides you move to another terminology, which is the noun phrase, which is a composition of several terms. So I found a little bit difficult to follow the aspect because in this slide you talk about terms and term clusterings, and then you go to noun phrase, which is a composed set of terms. And you do something, I have not really understood. If you first build noun phrase and then you cluster noun phrase. And the second point is that you cluster again something, I don't know if terms, noun phrase and so on, by using LDAs, so by using subjects, which are defined before. And even this is a little bit known. So LDAs is a little bit known. It's something that is a technique that which is known. And so my feeling is that I really not from somebody that is not aware in deep details of real work. I had some difficulties to understand the real contribution of it, right? Because all these techniques are known, and there are some mismatches in terminologies which prevents deep understanding when you see for the first time these kind of things. And again, on the second contributions, if I understood a little bit, you want to adjust to some extent the topics, because what I think is that if you have to know the topics before, so in the first step, in the first contribution, you have to know to list your topics. Maybe the ontology, which is resulting from this kind of things, is biased in the sense that the topics, if are used as a concept, are defined before. So the ontology, which is resulting from the discovery, may be biased by the topics that you defined before. Then what I understood is that then you adjust, or I don't know exactly what you do, but you adjust the topics by using core concept. And again, you come back to LDA, but again, I don't really understood which kind of techniques and which kind of knowledge you need to do that in a proper way. And finally, you move to the taxonomy discovery, but from my point of view, again, I think that this kind of discovery, this kind of techniques is very known, right? When you have a composite terms, you take a part of the terms just to build the artificial, I may say, taxonomy, which is very useful and which is recognized as a very useful techniques, but it is very known. I think that is very known. And then you may use something else, some external knowledge to link terms and to find the relationship. But I think that this is the background knowledge that can be used again for discovering technologies, the taxonomies. And also that is a little bit known. So I had some difficulty to understand which is the deep contribution in this about what you present, because it seems to be that several things are known, and again, as people that is not aware of in details of your work, most of the things are more or less known. So it's I don't know if you have some answer for me, but well, that's my question. What is really known with respect to the state of the art in the both contributions?
Okay, thank you for Professor Bechu. Yes, it is a really tough question, and it is the thing that my professors Mounira and Fabrice is always asking me to distinguish. And I will give more ideas about your questions. So at first, in contribution 1, there is 2 parts. The first part is the term clustering framework. The thing that is already known is that we have known that there are so many term clustering methods. And my contribution is that we make a research on those common term clustering methods and try to clarify the necessary stage when we are using the typical clustering scenario. And also, we try to explore the different possibilities in each stage. For example, we know that there's 4 stages for term clusters that we cannot skip. And then, for example, in stage 1, from my discussions in the thesis and from our hypothesis, we thought the noun phrases and the verb preposition combinations perhaps could play the major roles in the corpus. And in the stage 2, we try to provide what kind of representations that we thought is quite important in our thesis. So we provide these 3, and according to this, we also propose our own representations, and we also try to make the different variants of the representation and compare to our proposed representations with the previous already existing representations. That is one kind of contributions inside the framework. And
but for instance, here you
yes?
talk about word, when the matrices that you've shown are about word, and then you move to the noun phrase, right?
Yes.
But there is a big difference, because building a noun phrase may be difficult, and which is, for instance, the representation that you use. It is a representation of word, it is a representation of a noun phrase or whatever, because it is really not understandable from my point of view, but well, because all the examples are about word, and then you move to noun phrase, which is not the same thing.
Yes, I understand. Yes, I think that is a kind of mismatching, because the example I provide here in the rows is nouns, and the column is a verbs. And in my real proposals, I use the noun phrases as the rows and the verb preposition combinations as the column. Perhaps that is a mismatching that is pose some issues for you to understand this kind of my contributions. And if I continue, when I finish this kind of contribution here, this in the 1.1, I go to 1.2. 1.2 is that I using the thing exists that the topic embedding distributions have already exist once we get the result of LDA. And my proposal is try to figure out the problems and to figure out how to define the significant topical clusters, and if we want to get the topic cluster at the end, whether it is or what kind of pruning rules for us it is acceptable. So I try to using this kind of idea to provide answers for these two problems when we are trying to using the LDA as a clustering strategy. That is 1.2 contributions. And for the contribution 2, the 2.1 is about to, as you said, to add some barriers when we are training the LD. And I introduced that there has already existed two main directions to add our prior knowledge on LD. One is on algorithms, another one is on the documents. And our purpose here is try to propose the strategies to adding the prior knowledge in the document level. For example, here. We try to using the extra knowledge we got from the document and add them to the document as the prior knowledge. And this is our proposal. And here we try to compare our, at this time, we found that we have so many approaches. And we also found that we can define so many cases over the document. So our contribution here is we combine all the cases and the approaches together, which is came to here. And we try to distinguish what kind of cases combined with approaches could achieve the best result according to our prior knowledge embedding method. And then we found our best options. And at that time, we try to compare the already existing algorithm, such as seeded LD or zlib ID, and try to compare the result of them. And let's came back to the 2.2 of my contribution. Is about the taxonomic relation discovery. I have to admit that, as you said, those kind of, for the first method for the taxonomy relation discovery was quite simple, and it's quite normal. Because as I talked, is that we are using the already existing methods or techniques proposed by the previous researchers, and try to discover relation to build our ontology at the end. I divide that we can use two different directions. One is using the previous method to discover the taxonomy relations in our text. Another one is making use of the existing knowledge bases to discover the relations. And I need to admit that 2.2 perhaps could not as a principal distribution, because we didn't propose anything. We just read the work from the previous and reuse their techniques to satisfy our needs at the end.
But if you come back to the approach that you used to integrate the embedded the background knowledge in the LDA, as you showed before.
Yes, here.
Yes, I don't really understand which is the approach. You move really fast these slides, and again, I am not aware of your work in depth, so it is needed to spend a little bit more time. But I don't really understand what is the way in which you really integrate the information, the data. So before applying the algorithms is another matter. But before applying the algorithm, which is the approach that you use, so what I see is that you have you present four types of action that you may perform, but then it is a little bit unclear from these slides and even from your speech what really is done, because when I see the approach 2, so you perform a replacement. But what does it mean? So and you mentioned the keywords, but what do you take from the keywords?
Okay, thanks for your question. It is really necessary to indicate what we got before we continue to the LDA training. So before LDA training, we have the reconstituted corpus, and this reconstituted corpus was constructed based only on non-phrases or the other things that is we will discuss later, but main part is a non-phrases. So we can see that from in the table, in the row of approach 1, in the column of examples, that is the example that what kind of non-phrases we include in one document. And in the approach 2, they are trying to recognize the keywords. For example, we recognize the keywords at support vector machine, and we replace it with the core concept. And
yeah, but sorry. So
yes.
What is the keywords?
Yes, keywords was defined in this slide. At first, core concept, as we have mentioned several times, is defined by the expert, and it does not so many words for one corpus. For the keywords, it is the extra information that is provided in advance from the document that we trained. Because the 2 corpus that we select, for them, they provide the keywords for that document already. So it is extra knowledge we got from the corpus.
Yes, but again, if you use keywords which are defined in some way and some by any people and so on, you may be biased, and the ontology may be not the right one, because this bias is not the right one.
Yes.
So because the problem is that for the targets, the target is building an ontology. An ontology, as been said before, is something that is well defined. It's not something, right? Because when you use several techniques coming from machine learning or NLP and so on, you need to extract information, but this information then are useful for several things, and they don't need to be structured in a well-defined structure and so on. They are just information that can be useful for further analysis, but they are raw information mainly. So then the problem is that if you use this raw information for driving your process, and this may be a big problem, because the resulting ontology contains this raw information, and the resulting ontology is this raw information is not well done, provide a final structure which is not very good. So that's a good, maybe a big problem if this plenty of information that are defined before and then you need in your process are defined by people which is not aware that you want to build an ontology, but the final results may be not so good. Because the concept of keywords is undefined, so yes, I may put some keywords out when I want to provide some meta information in a document. I can put some keywords, but often these keywords may not correspond to any knowledge categories or whatever. So if you drive your process in this way, I'm not so convinced that the result is very good, except if your keywords are very good. But in this case, it's simpler to some extent to build the ontology manually because you know the ontology.
Yes. Thanks for your remarks. Yes, it is a really major issue that I didn't consider much about that, but I can give you the idea about what I think about keywords and how I use it and what I try to use it during my thesis. At first, as you said, the keywords were the raw information, and we cannot ensure the quality about the information that they give to us, whether they are commit to the ontology that we got or not. And I think about this problem before, and I try to ignore the keywords and try to find the keywords by myself if I thought that is really related to the document. And in fact, I tried to using some taxonomic relation discovery techniques as I talked. I try to find the sub-concept about the concept in taxonomies. At that time, I consider what if they exist in the document, they will consider as the keywords of the documents because we have know that they have a strong relation to the taxonomies at the end. So at that time, they are kind of faithful information that we add to the document. But the thing is, I try to use it, and the first issue is this kind of keywords was unbalanced. So it means some documents it has keywords, some documents does not have. Some documents has many keywords, some documents have 0 keywords when we are trying to using these discovery ways. So and so that is the first issue. The second issue is that it will include so many human interventions during the prior knowledge embedding steps, because what we want for the prior knowledge is just from the information that we got from the corpus. And at that step, we don't embed so many ideas or barriers that is connected to the result that we want at the end. We want to keep this kind of precise to be standalone. But it also has problems, as you said, because our target was ontology. If we don't try to include the keywords that relate to ontology, the result perhaps is not good. I really admit with this idea. And I think that could be the next step if I want to enrich my work. Because I also get some advice from my Professor Mounira. And she asked me to whether I can use some extra knowledge, such as Microsoft concept graphs, to provide keywords when we feed this kind of documents, and to ask what kind of keyword that is related to the documents. This could also be one option, but this kind of these branches of this method was not included in the thesis that I finished right now. But it could be a really interesting directions.
Okay, thank you. So it's 11:30, so I stop here, and I give the floor to Mounira HARZALLAH, if she is ready for asking questions or commenting or provide some remarks.
Okay, thank you, Mr. President. Thank you, Ziwei. I don't have a question, but I would like to thank again the members of jury for acceptance to attend the PhD jury of Ziwei, and also for their relevant question and remarks during the Ziwei defense. I agree, of course, with them that the PhD thesis of Ziwei shows many research element axes that need to be further developed, more especially the use of deep learning for ontology learning as transformer or contextualist term, embedding, integrating also the embedding in LDA. And also we can integrate better human knowledge graph on ontology learning. Both are hot topics now in the ontology learning area. And with Fabrice, we hope that we get a new PhD thesis on that topics that will be co-supervised with the Professor ICHISE. And so for that, I would like to thank Ziwei for the initiation of the collaboration with Professor ICHISE. And finally, I would just mention that Ziwei has built manually the first level of taxonomies by herself. So she has done this work for obtaining the gold standard for each domain that dealt with. And indeed, she has classified each extracted term in a core concept class if a term refers to a core concept. That means if a term is a hyponym or a synonym of a core concept, it is classified in its class. And it was a very complicated task that took him her many times. So thank you. I don't have question, as I said before. Thank you, President.
Thank you. So the last set of questions come from Fabrice Guillet. Please, Fabrice.
Thank you, Mr. President. I don't know if you hear me because my mic was off at the beginning of the meeting. Is it okay now?
Yeah. For me.
Okay, thank you. Thank you. I was not sure. Okay, so thanks for your presentation, Ziwei. Well, I will say more or less the same as Mounira, and I don't have question to ask to you, of course, because I had many times to discuss with you before and to make you some recommendations and many things to do in the task of ontology learning. So I will join Mounira to thank a lot all the members of the jury to attend your defense and to also make the report about your PhD report. Thanks for their expertise, their question, very valuable questions, their comments and their advices for improving that works. And there is many possibilities and hard tasks to do again with to improve the ontology learning. Okay, I will just recall that you, before making the PhD, you were a student learning a double master in computer science, a master from the Shanghai Maritime University, and also a master, it was a doubling master with the one of Polytech Nantes, in the general topic of computer science, about computer engineering and multimedia. So at the beginning of your PhD, you were a beginner for machine learning and ontology learning and semantic web, but I think it was a real difficulty for you to start at the beginning of your PhD. And as far as I remember, you were 4 challenging issues to address, personal challenges, that domain issue, to be more comfortable with machine learning, with semantic web, and so on. The second one was a technical issue with, learning to code in Python, to manage the library, and to go into that very large framework for data science. And that was the second issue. The third one was the validation issue. And in that domain, it is very complicated. It is not easy to find a gold standard. And a part of your PhD consisted in building a gold standard. And that was not so easy, and that was taking a long time to perform it. And of course, the core challenge of the PhD, that was to make some more semantic clustering and to embed knowledge, prior knowledge, into the algorithm for ontology and learning and concept formation more specifically. So I want also to recall that you had the opportunity to work with Professor ICHISE during your PhD and during a research mobility in Japan. And perhaps you will have also future opportunity in that research group also. As Mounira said, your works open many possibilities for the future, specifically with graph embeddings, knowledge graph embeddings, perhaps with a GNN or deep embedding techniques like that. And also, I think about the semantic relevance of the topics and of the concept that we learn with that techniques to improve the results. So there are many works to do again, I think, in that direction. So thank you very much, Ziwei, for giving me the opportunity to progress on that topic of ontology learning. That was new for me at the beginning of your PhD, and to initiate the collaboration with Professor ICHISE also. So good luck also for the future. And at least I would like to thank give very big thanks to Mounira, whom I was very pleased to work with, and it was very interesting and very fruitful, that 3 years of work together. So thank you very much.
Thank you so much. Thank you for Fabrice and also for Mounira.
Thank you. So I think now we can move on the private meeting.
Yes. So we will leave for the time for deliberations in a private meeting, and we will be back, I think, in, I don't know, between 30 minutes and 1 hour. It depends on the time we need to make the deliberation, and we will be back there in some minutes. Okay, so see you next.
Okay. See you.
Bye-bye. Okay, so the president is in charge to deliver the decision of the committee. So I first read the report, and then I made the conclusion and the decision. So, Mrs. Ziwei XU, your thesis work in the field of artificial intelligence and focuses on the use of machine learning methods for the semi-automatic construction of modular domain ontologies. So you have presented your work in a clear and structured way, and you have been able to put in evidence the complexity addressed by these topics, by the topic addressed, sorry. In particular, you have been able to present several contributions, significant contributions. The first one was the comparison of text clustering approaches using an adaptive representations. The second one was the development of a framework for term clustering. And the third one was the reuse of LDA, taking into account expert knowledge and allowing to improve the performance of clustering in order to build an ontology. You showed encouraging results coming from different experiments made on several corpora. So the jury, the committee asked several questions and in a various on various aspects, and you have been able by your answer to show a very new knowledge of the technique used and developed. The committee, the jury, also highlight your ability to carry out a thesis work in a difficult pandemic context, requiring to adapt your work and organizations. So for all these reasons, I'm pleased to announce that we deliver you the degree of Doctor of Computer Science from the University of Nantes. And we welcome and we are happy to for this occasion, and we hope that your future will be successful and plenty of good things. Voilà.
Thank you so much.
Félicitations.
Félicitations.
Congratulations.
Congratulations.
Thank you. I need to appreciate more for my professors, for Mounira and Fabrice. Yes. Yes, it is not easy work, and PhD is not easy as well. I appreciate all your contributions for my professor and for the referee members to give me so many comments, and it is really worth it to take into account and help me to enrich my work. And also, I have a nice experience to have internship in Japan with Professor ICHISE, and also Professor BERIO is also my jury members for each years of the PhD defense, and he also provided me so many helps to give me comments in the physical examination of my PhD. And yes, I also thanks so much to France. And I came to France because I accept the department fundings when I was a master, and then accept the 3.5 years more financial fundings from the France ministries to give me a chance to have such a good conditions with good professors and good conditions and also good laboratory to pursue my work in PhD. And it is really worthy if I have another chance to choose whether I will choose to become a PhD in France, my answer will be yes. And thank you so much for your effort today. Thank you.
Congratulations again.
Congratulations.
Congratulations, yes.
It's a happy moment. Appreciate it now. And be relaxed.
The best moment.
Thank you. Thank
and
you.
all the best for the future, and of course, for you, all the best.
I wish you all the best as well.
Congratulations.
Thank you again for all the jury members. Merci Fabrice, Mounira et bien sûr Hedi, Giuseppe, enfin tous les personnes que je ne connaissais pas. Forcément.
C'est connu.
C'est un plaisir.
Merci à tous.
Merci.
Thank you very much for all of us. Very nice.
J'ai oublié Ryu.
Have a nice lunch.
Thank you,
Bye.
Professor ICHISE. Thank you. Merci pour tous. Merci beaucoup.
Bye.
Au revoir.
Au revoir.
Bye. Bye.